Hello friends, welcome back to my YouTube channel. In this class, I am going to discuss three more problems of chapter 7 of P.K.NAG's Engineering Thermodynamics book. That is question number 7.34, question number 7.35 and 7.36 I am going to discuss. And these questions are very important not only from GATE exam point of view but also from engineering services exam point of view. Before starting, I must say one thing to all of you: please do subscribe to this channel and of course like it and share it to your friends. Let's get started. The question number 7.34 is like this. A lump of ice with a mass of 1.5 kg at an initial temperature of 260 Kelvin. So the key points of this problem are: the mass of ice is 1.5 kg, which is at initial temperature of 260 Kelvin, melts at the pressure of 1 bar as a result of heat transfer from the environment. After some time has elapsed, the resulting water attains the temperature of the environment, that is 293 Kelvin. Calculate the entropy production associated with this process. The latent heat of fusion of ice is 333.4 kilojoule per kg. The specific heat of ice and water are 2.07 and 4.2 kilojoule per kg Kelvin respectively, and ice melts at 273.15 Kelvin. The saturation temperature is a function of pressure, and the entire process takes place at a pressure of 1 bar. So you are required to calculate the entropy production, or you can say entropy generation. Entropy production is same as entropy generation associated with the process. Entropy generation is the total amount of entropy that is generated during this process is always equal to delta S of universe. यूनिवर्स का मीनिंग ये नहीं है कि एंटायर यूनिवर्स हियर कंसिस्ट ऑफ द सिस्टम दैट इज द आइस एंड its immediate surroundings, and that system along with its immediate surroundings constitutes an isolated system, and that composite isolated system is considered as universe. Suppose this is system and its immediate surroundings. This is immediate surrounding. And this system and the immediate surrounding constitute your universe for the problem under consideration. This is your universe, and this universe can be considered as a composite system, and which is isolated, because every component of this process, whatever happens, is the ice melts by absorbing heat from outside, and no interaction takes place insofar as this composite system is considered with its surrounding. So whatever process takes place, that is confined within this system and its immediate surrounding. So this can be considered as an isolated system. So universe is always an isolated system. Universe is always an isolated system. So whenever entropy change of a closed system takes place, it takes place only due to, so change in entropy of any system in fact takes place through entropy transfer and entropy generation. entropy transfer होता है, नहीं तो इनसाइड में सिस्टम का अंदर एंट्रोपी जनरेशन होता है. So change in entropy is summation of change in entropy. This is delta S T is entropy transfer, and In fact, this is AST and entropy generation. अगर ये प्रोसेस रिवर्सिबल है तो एस जेन इज जीरो. इन केस ऑफ रिवर्सिबल प्रोसेस एंट्रोपी जनरेशन जीरो होता है. एंड एंट्रोपी ट्रांसफर कैन टेक्स प्लेस आइदर थ्रू हीट और थ्रू मास. And in case of a closed system, there is no mass transfer between system and surroundings, so this is zero. And in case of an isolated system also, heat interaction is not there, because in case of isolated system there is neither energy nor mass interaction, so this term is zero. So only delta S universe becomes, this is equal to entropy generation. Whenever in a question it is asked to find out entropy production or entropy generation, we can do it by calculating the delta S of universe only, whatever be the process. If you calculate change in entropy of universe, that will be your entropy generation during that particular process. So in this case also you are required to find out the entropy production. So what we will do is we will calculate the change in entropy of universe only, and that will be same as entropy generation during process. So entropy generation of system, delta S of universe is nothing but delta S of system plus delta S of surrounding. So first we will calculate the change in entropy of system, that is ICE, and then we will calculate the change in entropy of surrounding. Here what happens, ICE 1.5 kg of ICE, which is at initial temperature of 260 Kelvin, melts, and its melting point at 1 bar pressure is given to be 273.15 Kelvin. So when it goes from 260 Kelvin to 273.15 Kelvin, it is in the solid state, that is at ice. So first change in entropy अगर calculate करना होगा तो it can, insofar as the change in entropy of system, that is your ice 1.5 kg of ice, it consists of 3 stages. So first stage में जब आइस 260 केल्विन से 273.15 केल्विन, which is the saturation temperature corresponding to 1 bar pressure, जाता है, आइस जाता है 260 केल्विन से 273.15 केल्विन तक. ये एक स्टेज 1 होगा. अगर हम द प्रोसेस ऑफ entire process of ice changing from its initial state to final equilibrium temperature of 293 Kelvin, then it can be divided into 3 stages. So this is the first stage, change in entropy during first stage calculate करेंगे. And second stage में जब ice melts at constant temperature of 273.15 Kelvin, and during that process the state change takes place and ice is converted to liquid water, so by observing latent heat of fusion. Since no change in temperature takes place during this stage, it is called that heat is called latent heat. So यहाँ second stage होगा ये. हम third stage होगा जब water का temperature, once it absorbs latent heat of fusion, it is converted into liquid water. Then its temperature increases from 273.15 Kelvin to 293 Kelvin, because it is given in the question that after some time is elapsed, the resulting water attains the temperature of the environment, which is 293 Kelvin. So third stage में liquid water is heated. Now this is no longer ice. During this stage it is converted into water and its temperature is increased. Liquid water is heated from 273.15 Kelvin to 293 Kelvin. So if you want to calculate the delta S of system, here delta S of system means ice, here it will consist of change in entropy during three stages. Summation of change in entropies during three stages. First one is delta S1, change in entropy during first stage when ice is heated from 260 Kelvin to 273.15 Kelvin, and delta S2 is the change in entropy during phase transition, plus third stage is change in entropy when liquid water is heated from 273.15 Kelvin to 293 Kelvin. So this will be फर्स्ट स्टेज में जो चेंज इन एंट्रोपी होगा वो होगा डेल्टा S1 इज नथिंग बट m ऑफ आइस, बिकॉज स्टेज वन में वो आइस है, m आइस, स्पेसिफिक हीट ऑफ आइस dt. Delta S1 is nothing but integral of dq by t, and that is mc dt upon t. So since these two terms are constant, this can be taken outside. This is dt upon t. This is m ice, mass of ice, multiplied by specific heat of ice ln t. Initial temperature of ice is 260 Kelvin and final temperature is, saturation temperature is 273.15 Kelvin. This is, mass of ice is given to be 1.5 kg. Mass of ice is given 1.5 kg. So 1.5 kg multiplied by specific heat of ice is 2.07 kilojoule per kg Kelvin. It is given in the question. Specific heat of ice, this is 2.07 kilojoule per kg Kelvin. So this multiplied by ln 273.15 divided by 260, and this will be a pure number. So on multiplying, energy unit of this term will be kg cancels out, the unit will be kilojoule per Kelvin, because this term has no units. So now answer is 3.105 multiplied by 0.0493. This is equal to 0.1531 kilojoule per Kelvin. Similarly, during stage 2, when the phase change of ice takes place, when during the saturation temperature of 273.15 Kelvin, when ice is converted into water at constant pressure of 1 bar. So at that time the change in entropy is nothing but latent heat of fusion, mass of ice multiplied by latent heat of fusion divided by T saturation, because temperature does not change during this process, during this stage. So this is how we calculate the change in entropy, and this is equal to 1.5 multiplied by latent heat of fusion of ice is given to be 333.4. This is given 333.4 kilojoule per kg, latent heat of fusion of ice, So divided by 273.15, and unit will be kilojoule per Kelvin, and this is equal to your 1.83 kilojoule per Kelvin. So next, the third stage, when the temperature of water increases from 273 point, now it has attained the liquid state. Now it is no longer in the solid state, that is ice. So delta S3 will be M liquid, C liquid, or you can say M water. Now M water, C specific heat of water dt upon T, that is M water, C water ln T, and initial temperature in this case is 273.15, and final temperature, that is the environment temperature, 293. So this becomes 1.5 multiplied by 4.2 kilojoule per kg Kelvin, that is specific heat of water. It is also given 4.2 kilojoule per kg Kelvin. So multiplied by 4.2 ln 293 divided by 273.15. So this becomes 0.4419. Again unit will be kilojoule per Kelvin. So now on adding these two terms, delta S1, delta S2, delta S3, you will find the change in entropy of system. So delta S system, this is delta S system. Delta S system will be, that is ice, delta S of ice, delta S1 plus delta S2 plus delta S3. Change in this is change in entropy during first stage, this is during second stage, and this is third stage. So on adding these three terms, this is 0.1531 plus 1.83 plus 0.4419 kilojoule per Kelvin, and this is equal to 2.425 kilojoule per Kelvin. This is the change in entropy of system. But we have to calculate the delta S of surrounding also, so that we will be able to calculate delta S of universe. Whatever change, whatever heating takes place, or whatever phase change takes place, that of ice, for that heat is needed, and from where that heat comes, that comes from surrounding only. So अगर हम चेंज इन एंट्रोपी ऑफ सराउंडिंग कैलकुलेट करना चाहते हैं, तो ऑब्वियसली इट्स टेम्परेचर डज नॉट चेंज बिकॉज इट इज ए रिजर्वर in this case. So whatever heat comes from this, and if you want to calculate the change in entropy of surrounding, that will be minus of heat supplied to ice, heat supplied to ice, or you can say heat absorbed by ice, divided by T surrounding, divided by T surrounding, because this is how we calculate the change in entropy of reservoir. Temperature is constant, so no integration is required. Minus of Q supplied to ice, or you can say Q rejected by surrounding. You can say Q rejected by surrounding. Since it is rejected, minus sign is put before it. So delta S surrounding will be minus of Q, that heat supplied or heat absorbed by ice to come to that final state, divided by T surrounding. Of course, it has to be expressed in terms of Kelvin. So what is the heat supplied? Heat supplied is again during these three stages. So, or you can say heat absorbed by ice. This is same, Q supplied to ice is same as Q absorbed by ice. This is again in three stages. First, when it is heated from 260 to 273.15, you consider the specific heat of ice only. So for that, 1.5 multiplied by 2.07, because this is the specific heat during ice. When the material is in, when the substance is in solid state, the specific heat is 2.07 kilojoule per kg Kelvin. 273.15 minus 260 plus, when the phase change takes place, it absorbs latent heat of fusion. So mass multiplied by latent heat of fusion, that is 333.4, plus when the liquid water, now it has attained the liquid state. When the liquid water is heated from 273.15 to 293 Kelvin, then what is the heat absorbed? The specific heat will be considered that of water, that is 4.2 multiplied by 293 minus 273.15. This is equal to 665.9857 kilojoule. So delta S of surrounding will be, delta S of surrounding will be minus 665.9857, and surrounding, the temperature of surrounding is 293 Kelvin. So this is kilojoule, this is Kelvin, and this is minus 2.425 2729 kilojoule per Kelvin. But our ultimate objective is to find out delta S universe, which will be same as entropy generation. So delta S universe will be delta S of system plus delta S of surrounding. This will be 2.425 plus minus 2.2729. This is kilojoule per Kelvin, and this answer is 0.15 this is 0.1521 kilojoule per Kelvin, and this is same as entropy production during the process, and since this is greater than 0, this is an irreversible process. So the question asks to find out the entropy production, and entropy production or entropy generation will be same as delta S of universe, change in entropy of universe, and that is equal to 0.1521 kilojoule per Kelvin. So next question is question number 7.35. You see, an ideal gas is compressed reversibly and adiabatically from state A to state B. Ideal gas is compressed reversibly and adiabatically from state A to state B. It is then heated reversibly at constant volume to state C. After expanding reversibly and adiabatically to state D, such that Tb is equal to Td, the gas is again reversibly heated at constant pressure to state E, such that T is equal to Tc. Heat is then rejected reversibly from the gas at constant volume till it returns to state A. Express Ta in terms of Tb and Tc. And if Tb is equal to this much and Tc is equal to this much, estimate Ta. So first we have to derive an expression of Ta in terms of Tb and Tc, and then just by putting these values in that expression we can find out the Ta. So this question is divided into two parts. First we have to derive an expression, and in the second part we have to just put the numerical values to find out Ta. Since Tb and Tc are given and gamma is also given, so first our objective is to find out the temperature, find out an expression for temperature Ta in terms of Tb and Tc. So first we have to plot the Ts diagram issue. Ideal gas is compressed reversibly, this is temperature and this is entropy. State first is ideal gas is compressed reversibly and adiabatically from state A to state B. You know, when a gas is compressed reversibly and adiabatically means it is an isentropic process. So during this process the entropy remains constant. Any process which is reversible and adiabatic means it is an isentropic process. So entropy remains constant. So the process will be a vertical line on Ts diagram. So this is A, this is B. And you can say this is entropy is equal to constant line. Since this is entropy axis and this is temperature axis, this has to be a vertical line. And then you see it is then heated reversibly at constant volume to state C. Constant volume to state C. So constant volume line on Ts diagram is like this. Constant volume. This is constant volume. And up to point C. Then after expanding reversibly and adiabatically to state D such that Tb is equal to Td. So now this is point C. Here this is the constant volume heating process, so temperature increases, and you know during compression also temperature increases. So that's why A to B is like this. So now the reversible adiabatic expansion, that means isentropic expansion takes place, and you know during expansion temperature decreases. So it is given that at the end of this process CD, when the temperature Td is attained, and that Td is nothing but same as Tb. So Tb, this is your B, so Tb is same as Td, so this is your D. This is again a isentropic process. This is isentropic expansion. Now Cd. Next process is the gas is again reversibly heated at constant pressure to state E such that Te is equal to Tc. Now again another heating process is there, and this is a constant pressure heating. So this is the final point. This line is for pressure is equal to constant, and this heating takes place in such a manner that at the end of the process Te becomes Tc. This temperature is same as T. This is state E. This is state. Now heat is then rejected reversibly from the gas at a constant volume till it returns to state A. Now this is a constant volume process. This is a constant volume process. This is a constant volume heat rejection process. E to A. So this completes a cycle from A to B, reversible adiabatic compression. This is constant volume heat addition BC. This is CD is again adiabatic expansion isentropic process. Entropy is constant. And then D2E is the constant pressure heat addition process. And E2C is a constant volume heat rejection process. So now this is a cycle. So you have to express Ta, and one thing is Tb is equal to Td and Tc is equal to Te. That is given. You see, this is given in the question. Tb is equal to Td and Tc is equal to Te, given in the question. And that is also reflected on the diagram here, on TS diagram. Tb is equal to Td and Tc is equal to Te. So now you see, and change in entropy, we know that cyclic integral of ds is 0. Cyclic integral of any property is in fact 0. And since it completes a cycle A to B, B to C, C to D, D to E and E to A. So that's why we can say that delta S of AB plus delta S of BC plus delta S of CD plus delta S of DE plus delta S of EA is equal to 0. But you see, AB and CD are isentropic processes, AB and CD. So we know that for an isentropic process, and change in entropy is always 0. Delta S AB and delta S CD are 0. So now the remaining three terms, if added, also results in 0. So from this, what we find is delta S of BC plus delta S of DE plus delta S of EA are 0. So now we know that this equation is applicable for all process, be it constant pressure or constant volume, whatever be the process. So this is for du for an ideal gas is CBDT. TDS is equal to du plus PdB, and another equation is TDS is equal to dH minus VdP. Then you can say this is du plus VdB. So this is equal to mCV dt plus PdB, and this can be written as mCP dt minus VdP. You see, for constant volume process, for constant volume, these two equations can be used for any kind of processes, and to find out the change in entropy. So of gas, of course, constant volume process. For constant volume process, dV terms becomes 0. So TdS is your mCV dt, from which ds can be obtained like this: mcb dt upon t. So if you want to calculate change in entropy, that will be integrate ds and integrate right hand side, that will be mcb dt upon t. This is mcb ln t. If you take the integration limit, that will be mcb ln t, limit is from t1 to t2, then mcb ln t2 by t1. This is the change in entropy for a constant volume process. Mass multiplied by cb, that is specific heat at constant volume, multiplied by ln T2 upon T1, final temperature by initial temperature. And similarly for constant pressure process, if you want to calculate the change in entropy, this equation can be used conveniently, that is TdS is equal to dH minus VdP, that is mcp dt minus VdP, and for constant pressure process this term becomes 0. Now ds becomes mcp dt upon t, and just like what we did for constant volume process, change in entropy will be nothing but mcp ln t2 by t1, So now these three processes, out of these three processes, two are constant volume processes like Vc and Ea, and De is constant pressure process. So now delta S Bc will be how much? So if you calculate the change in entropies, that expression will be like for process Bc, delta SBC is a constant volume process. BC you see is a constant volume process. So delta SBC will be nothing but SC minus SB is equal to MCB dt upon T, and the limit is from TB to TC. This is equal to MCB ln TC upon TB. This is the change in entropy during BC. Similarly, change in entropy during the process DE will be MCP ln, because it is a constant pressure process, ln TE upon TD. Similarly, delta S of EA, it is a constant volume process again. It is a constant volume process. It is a constant EA is a constant volume process. That will be MCB ln TA by TE, final temperature by initial temperature. So now summation of these three terms are 0 as per your equation. From this equation, delta SBC plus delta SDE plus delta SEA is equal to 0. So just by putting these values, I will find MCB ln TC upon TB plus MCP ln TA upon TD plus MCB ln TA upon TE equal to 0. So now MCB ln TC by TB plus CP ln TE upon TD plus CB ln TA upon TE is equal to 0. And you know M cannot be 0. So for this equation to be satisfied, this term within the bracket has to be 0, which implies CB ln TC upon TB plus CP ln T upon TD plus CB ln TA upon TE equal to 0, which implies ln TC upon TB to the power CB plus ln T upon TD to the power CP plus ln TA upon T to the power CB equal to ln 1. 0 is nothing but ln 1, which implies ln Tc upon Tb to the power Cb T upon Td to the power Cp Ta upon T to the power Cb is equal to 1. Sorry, ln 1. And from this I can write Tc upon Tb to the power Cb T upon Td to the power Cp multiplied by Ta upon, this is Te upon Td, Ta upon T to the power Cb equal to 1. And on multiplying these terms, this becomes Tc by Tb, Tc by Tb Cb multiplied by Te is given in the question that T is same as Tc. So this is Tc by Td to the power Cp multiplied by Ta divided by T. T is same as Tc and Tb is same as from the diagram. From diagram we know that Tb is equal to Td and Tc is equal to Te. So by putting this we find that Tc by Tb to the power Cb multiplied by Tc by Tb, because in place of Td I can write B multiplied by, and in place of E I can write Tc, because Ta is equal to Te is equal to Tc. So now this is equal to 1. Or I can say Tc by Tb to the power Cp plus Cb is equal to 1 divided by Ta by Tc to the power Cb. So I can say Ta by Tc to the power Cb is equal to 1 divided by Tc by Tb to the power Cp plus Cb. This is equal to Tc by Tb to the power minus Cp minus Cb, or Ta to the power Cb is equal to Tc to the power Cb multiplied by Tc to the power minus Cp minus Cb divided by Tb to the power minus Cp minus Cb. This is equal to Tc to the power minus Cp minus Cb, Cb cancels out, Tc to the power Cb into Tc to the power minus Cb is Tc to the power 0, that is 1. Tc to the power minus Cp divided by Tb to the power minus Cp minus Cb. So this becomes, you can say Ta, this is equal to Tb, ये माइनस पावर में है तो ऊपर चला जाएगा, Tb टू दी पावर Cp प्लस Cb डिवाइडेड बाय Tc टू दी पावर Cp, ये माइनस में है तो नीचे आएगा. So now Ta can be expressed as, if x to the power y equal to z, then x is equal to z to the power 1 by y. By using this, Ta to the power Cb is this much. So Ta will be Tb Cp plus Cb to the power 1 by Cb, and that becomes, this is, and Tc Cp to the by Cb, and this becomes Tb to the power Cp plus Cb divided by Cb, Cp by Cb plus Cb by Cb. This is gamma plus 1 divided by Tc to the power gamma. So this is the final expression. Ta is equal to Tb to the power gamma plus 1. Gamma is ratio of specific heat, Cp by Cb, it is, and divided by Tc to the power gamma. And in the second part, you see in question, it is given that to find out Ta, we have to put the given values of Tb and Tc, and the gamma value of gamma is also given. So Ta will be, Tb is given to be 555 Kelvin and gamma is given to be 1.4. So 1.4 plus 1, that is 2.4, divided by Tc is given to be 835 Kelvin to the power 1.4, and this comes out to be 313.28 Kelvin. So this is the final answer for TA. So next question is question number 7.36. The question is like this: liquid water of mass 10 kg and a temperature 20 degrees Celsius is mixed with 2 kg of ice at minus 5 degrees Celsius till equilibrium is reached at 1 atmospheric pressure. Find the entropy change of the system. Cp of water and Cp of ice are given, and latent heat of fusion of ice is also given. You see, so to find out the final equilibrium temperature, we must know that what is the final state. Whatever heat the liquid water will supply to the ice, obviously the liquid water will supply heat to the ice, then only the heat will be lost by water and heat will be gained by ice, so that ice can melt, and it can also further go by observing latent heat of fusion. It will reach at the liquid state, and then also it can its temperature can go up if the heat supplied by liquid water is more than that is required to attain the saturation state and getting melted. So from this, first thing we have to decide what is the final state of this ice. So to know that, heat rejected, supposing that ice, to what is the heat required for ice to reach the saturation state, or and then to phase change takes place, what is the amount of heat required. So first we know that heat rejected by liquid water when it reaches 0 degrees Celsius. 0 degrees Celsius means it is in the liquid state. So that heat is 10 into 4.118, because the specific heat of water is 4.18 into 20, because the initial temperature is 20 degrees Celsius. So 20 minus 0, that is 836 kilojoule. But heat required to melt ice, of course after bringing it to the saturation temperature, is 2 into Cp of ice multiplied by, now the initial temperature of ice is minus 5 डिग्री सेल्सियस. सो माइनस 5 से 0 तक लेने के लिए इतना हीट चाहिए. Cp ice क्यों मल्टीप्लाई किए? बिकॉज ड्यूरिंग दिस स्टेज ice substance is in the solid state. Once it reaches the liquid state, once it reaches the saturation temperature, it will also require some latent heat of fusion. This is on adding these two terms, Cp of ice you put 2.09, this term comes out to be 688.9 kilojoule. Since this amount of heat is greater than this, obviously the ice will finally the ice will attain the liquid state, and obviously its final temperature will be higher than the saturation temperature, and it will be greater than the 273 Kelvin, that is the saturation temperature. It will be higher than that, and also the liquid water will also reach at that temperature. So what will be that temperature? Let TF be final equilibrium temperature. Final equilibrium temperature in Kelvin. So now we have to calculate final equilibrium temperature by applying the equation that heat lost by water is equal to heat gained by ice. Heat lost by water is equal to heat gained by ice. Heat gained by ice. So by equating that, mass of water is 10 kg, 10 multiplied by specific heat of water is 4.18, initial temperature of water is 20 degrees Celsius, so 293 Kelvin minus TF. This is the heat lost by water, because the final equilibrium temperature is TF and the final state is water. It will remain in the water state. It will not go to any other state, that is solid state. By giving away heat also, it will remain in the water state. So this is the amount of heat lost by water. And heat gained by ice is 2 kg of ice, 2 into 2.09. This is given in the question that mass of ice is 2 kg, 2 kg of ice at initial temperature of minus 5 degrees Celsius. So 2 into 2.09 minus 5 से 0 डिग्री सेल्सियस तक जाने के लिए temperature difference will be same 5. Even you take in the temperature in terms of Kelvin also, the temperature difference will remain same, that is 5, plus 2 into latent heat of fusion of ice is given to be 334, plus 2 into 4.1. Once it reaches the liquid state, specific heat will be 4.18 into TF minus 273. On equating this, you will find that final equilibrium temperature will be, just equating this, 275.93 Kelvin, or you can say 2.7 275.93, or you can say 2.83 Kelvin degree Celsius, 2.83 or 81 degrees Celsius. Or you see, we are calculating in terms of Kelvin, so no necessary to, it is not necessary actually to express it in terms of degrees Celsius. So this is 275.93 Kelvin. Now we have to calculate change in entropy of water and change in entropy of ice, and so that we will add those two terms and find out the change in entropy of system, which is you are required to find out. Find the entropy change of the system. So delta S of water is nothing but mCp dt upon T, that is mc ln T final temperature by initial temperature, 10 into 4.18 multiplied by ln 275.93 divided by 293, that is minus 2.509 kilojoule per Kelvin. Similarly, if you want to calculate delta S of ice, here also there are three phases. So first, when ice is heated from 268, that is minus 5 degrees Celsius, to saturation temperature, that is 0 degrees Celsius, mc ln final temperature is 273 divided by 268, plus during the phase transition latent heat of fusion divided by saturation temperature is 273, plus during when this new water, the water that has been produced by melting ice is heated from 0 degrees Celsius or 273 Kelvin to final equilibrium temperature, that is 275.93. So what is the change in entropy? 2 into 4.18 multiplied by ln 275.93 divided by 273. This is equal to 2.6132 kilojoule per Kelvin. So delta S of system will be delta S of water, and assuming that this whole process takes place in an insulated surrounding, that means the system, this is ice and water constitutes an isolated system. So no interaction, heat interaction or any other energy interaction takes place between this combination of systems, that is ice and water. This is a mixing process and which takes place in an adiabatic manner. So delta S of water plus delta S of ice. This is equal to delta S of water is minus 2.509 minus 2.509 plus delta S of ice is 2.6132 kilojoule per Kelvin. So this is equal to 0.104 kilojoule per Kelvin, and this is equal to, in terms of joule, that is 104 joule per Kelvin, just by multiplying 1000. So that's all. Thanks for watching.